About the header format for IP, and we have mentioned the function of each of these fields, and we have highlighted these three flags which are used for fragmentation, and we said that fragmentation is one of the Bismillah ar-Rahman ar-Rahim. So last time we functions that IP version 4 performs to adapt to the different networks in each link, because IP itself covers different types of links. So this one may be wireless, this is maybe fiber optics, this is maybe Ethernet, and so on. For each one, there is what we call maximum transmission unit. So for example, for Ethernet, maximum transmission unit that you can send from the data link layer point of view is only 1500 bytes. This is the maximum transmission unit. So if you are coming from a link which has more maximum transmission unit, higher maximum transmission unit, and you are going through an Ethernet link, then you have to fragment. You have to do some fragmentation, which means that the packet, the big packet itself from this link to this link has to be broken and fragmented into multiple what we call fragments. By the way, this fragmentation has been totally removed in IP version 6. There is no such thing in IP version 6. There's no fragmentation whatsoever. So different links have different types of maximum transmission unit, and therefore we need to do fragmentation. So the way fragmentation is done is that on one link, once we discover that we need to do fragmentation, then we do the fragmentation, and then when we go to the other link, if we find that we go from a lower MTU or maximum transmission unit to higher MTU, what do we do? Huh? Max. We don't do that. We don't do defragmentation. Once we do fragmentation, the only place where we do defragmentation is where? At the ultimate receiver. Okay? So once we do fragmentation, we don't do defragmentation. Why? Because this way we have to do defragmentation, and then possibly we'll have to do fragmentation again, and defragmentation, and that increases the complexity and increases the delay. So once we do we don't have any choice to do fragmentation, because we're going from a higher maximum transmission unit to a lower maximum transmission unit. So in that case, you have to break down your box into smaller boxes. You have no other option, right? But when you go from a low to high, okay, so I wanna send smaller chunks as opposed to big chunk. I have the choice to do that. Okay, so that's why we do fragmentation. We don't do defragmentation until the very last ultimate receiver. So remember that. So the reassembling of these fragments happens only at the final receiver, but the fragmentation can be done at different stages. Every time you go from a higher to lower, you do a fragmentation, but the defragmentation is done once at the very end. So the way or the mechanism that we do that is that when the packet is large, so assume that we have a packet of 4,000 bytes. 4,000 bytes. So these 4,000 bytes, we are going through a link with maximum transmission unit of 1,500, which is Ethernet. So we're going from, let's say, like fiber optic link with maximum transmission unit of 4,000 bytes. We're going through a link with MTU of 1,500. So in that case, we have to do defragmentation. So the way we do that is using these three fields are very important: the identifier field, and the flag, and the fragment offset. Those are three fields which are very important. So each packet will have a sequence or identifier number. So this sequence number will be replicated to all the fragments, which means that all these fragments, they belong to this packet. Okay? So this identifier will link these fragments to this packet. So at the very last end, when we do defragmentation, we know that all these fragments need to be kind of consolidated. Okay? But this consolidation can happen in different ways. Which one comes before which? Okay, we have to do reordering. So we need some extra information to do that. And these are these two fields that we use them for ordering. So the fragment flag indicates that I still have more fragments for you. Okay, so this tells me that if this flag is 1, this means that this is not the end of these fragments. There are more fragments coming. Okay? Once it's set to 0, this means that, okay, I finished sending all the fragments. Okay? So is this enough to consolidate the fragments at the receiver? No, because I have many fragments with flag 1, 1, 1, 1, but I don't know which one comes before which. Okay, so I need extra level of information, and that's what we call the fragment offset. The fragment offset tells me where this fragment is in the original packet. And it's not ordered by 0, 1, 2, no. It's actually a pointer to where this fragment is in the original packet. So the first packet will always start from 0, which means that this fragment is the first fragment, and it starts from location 0. Then the second fragment is in the location 185. Remember, this 185 has to be multiplied by 4 to know at which location exactly in the original packet that this fragment should be put at. So this fragment offset will allow me to put the fragment in the original location to form the actual packet. So this actually allows the fact that these fragments might arrive unordered. Okay, so I can fill using this fragment offset. I can fill in the location, and I have some gaps, and then I find the fragment and I fill the gaps until I find that the packet has been formed completely, and then I can send it up.
Is it always increasing to the end, like the offset?
The offset, of course, the offset is growing.
It doesn't have to be like an order. As long as it is increasing, then it's increasing.
Yes, but remember, this is actually the exact location of this fragment in the original packet. So this is location 0, this is 185, multiply this by 4, and this will be the byte number 185 plus 185 times 4. So that's exactly the location of this fragment in the original packet. And this is actually 370 multiplied by 4, and then we put it in the original packet. Until you find that you fill all the gaps, which means that the packet is complete. The flag is 0, which indicates to you that everything is finished, and I send all the fragments, so you can send it up in the layer.
These 3 fragments belong to the original packet in the
Right.
yes?
Right.
But what the sum of the length is 4040, and the length of 4000.
Where is 4040?
1500, 1500, and 1040.
Right. 1000. Sorry, 1480. Sorry.
The length of the fragments.
20 bytes for the
Yeah. So this, remember, the length is the length of the data part and the header, and the header is 20 bytes. So this length contains the size of the header. So basically, if you want to know the exact data size here is the 3960 or 980 in that case. So this is the data part. Okay, so this needs to be divided into 3 parts. So you have 1480 is this one. So you take 1480 from this, and this will be the first fragment. Add the header, so the total length will be 1500, right? So the second one, another 1480, add 20 bytes to it, then it becomes 1500, and so on, until we come to the last one. So the last one, the remaining part, is 1020. When you add the header to it, it becomes 1040. So all these lengths, they add the header length to it, because if you remember, the field length in the packet header includes the length of the data and the header. Okay? So that's how we do fragmentation. And as I said, in IP version 6, we don't have fragmentation.
This 185 also, I'm not able to calculate how it is coming 185. So let us, for first it is correct that it is the first frame, so it is 0, offset is 0, but for second it is coming 185. How it is coming 185, I'm not understanding. So if 1480 bytes are there, divide by, if you will make 8 also, it is not coming 185.
So 1480
Divided by 8 is not.
divided by 8 is not this?
No. Huh?
We can...
No, I think no, my calculation mistake. No, no.
It's correct?
Okay.
Okay.
What is the 8? Where did the 8 come from?
This 8? This is how the fragment offset is calculated. It's actually the number of 8 bytes word. Remember, we said that there is a header length, which is the number of 4 byte words, right? So the fragment offset is the number of 8 byte words. Okay. So sometimes they try to shorten the number that you use for the fragment offset, so that you can shorten the number of bits used for that. So as long as the number that you use in terms of size is divisible by a number, so I can say, okay, so this number has to be divided by 8 to shorten the number of bits that I use. طيب, so now for IP version 4, we talk about subnets, which is of course a topic that some of you are familiar with. So for subnetting, if I have a big network, and this network has this address, so I can divide this network into subnets, and I can take, of course, if I have this address and this address is /16, which means that those 2 bytes are for network and the rest is for host, then I can take these 16 bits and divide my network into subnets. In that case, I can use, for example, these 8 bits to give like a subnet number. So this network will be 223.1.1, and this network will be 223.1.2, and this will be 223.1.3, and so on. So I can divide my big network into subnets. And of course, subnets are a very important concept because it actually isolates the broadcast domains of this big network into smaller broadcast domains, and that enhances the performance of the communication significantly. So there are some benefits to why I actually do subnetting. This is also good from security perspective, so that if you have this network isolation, if you have any problem in one of the networks, it gets isolated from all the entire network. So you have the router acting as an obstacle from the communication from one subnetwork to another. The router has some control on how to control the traffic. And even if you send some broadcast messages, the router can suppress these broadcast messages that are coming from one subnetwork to another. So you have some control. So that's the basic Of course, subnetting is a big topic that's covered completely in other introductory courses. So in the past, the way that we used to allocate these IP addresses through a very they call it discriminatory kind of address allocation by dividing the address domain into classes. We say class A, class B, class C. So in that case, the network part is either 8 bits, 16 bits, or 24 bits. We don't have anything in between. And that led to IP address exhaustion to be very, very fast, right? So you have very, very few organizations all over the world that are class A. In fact, you have 127 organizations worldwide class A. And these have more than 50% of the address domain worldwide. And these are very few organizations. So the way that they allocated IP address in the past was very coarse. They call it very coarse allocation, not fine-grained. So the CIDR, or classless interdomain routing, came as a new mechanism to use a specific subnet mask with the IP address. But where is the subnet mask stored? It's actually in the routing table, not in the packet. We don't store subnet mask in the packet, right? But we store it in the routing table, right? But this subnet mask is allowed to grow at the bit level, not at the byte level. So we don't have 8, 16, 24. No, we can have now 17, 18, 19, and so on. But this will require new extra information that we need to have in order to facilitate the separation of the network part from the host part, which is what we call the subnet mask. And we store that in the routing table. So the address has become a.b.c.d slash something. And slash something, this is the subnet mask that gives us the size of the network part from the left-hand side. So if this is, for example, slash 24, this means that the first 3 bytes from the left are the network part, and the remaining part is for host, and so on. Okay, so now we can have something like slash 23, slash 22, and so on. So that gives us more granularity. So instead of the coarse allocation, now we can be more fine-grained. But that's not enough, because nowadays we are still in shortage in terms of IP allocation. So that did not solve the problem significantly or radically. It solved the problem in a step kind of improvement, not drastically. And that's why some people took the evolutionary approach of enhancing the IP address allocation through CIDR and later on through variable length subnet mask and through some other techniques. But some people have taken the revolutionary school of designing IP address version 6. So that will solve the problem on a very, very long term. Okay, but unfortunately we cannot use IP address version 6 in a comprehensive way or on the internet, because that will require a huge amount of modifications that we cannot afford at this point. And we'll talk about this. So how does network get subnet part of the IP address? Well, for small organizations like UU, the way that you get the network part is from Ooredoo. But how does Ooredoo get their own network part? Well, you can say that this is from tier 1 service providers. So how does the tier 1 service? So you end up with eventually you end up with some organizations that are responsible for allocating these network parts worldwide. These are the organizations that give some allocation of IP addresses to tier 1 service providers, which in turn they give this. They subdivide this address allocation into smaller parts and give that to tier 2 service providers and tier 3 until it goes to consumers or to users like ourselves. Okay, so you get a specific ISP block, and then you can borrow some part of this, like for example 4 bits that can be used for subnetting, which will give you 16 different subnets. So an ISP with 4 bits of subnet part can allocate 16 subnets. So they divide their address into 16 subnets, and then they evaluate the address range for each of these subnets. There is another very important concept which is probably not covered in 455 or any introductory course. The way that we allocate the IP address is hierarchical, in the sense that not only do we do address allocation, but we can use the concept of route aggregation, or sometimes they call it route summarization. Okay, route summarization talks about the fact that if I'm a service provider here, or like a QU, and I have routers, and I have some subnets. As we can see, these subnets are allocated IP addresses which are kind of contiguous. Okay? Contiguous يعني the IP address is continuous in order, in a way, right? So when this ISP tries to send the routing information to other parts of the internet, so what we can imagine is that we can say, okay, if you want to send traffic to this network, send to me. If you want to send traffic to this network, send to me. If you want to send traffic to this network, send to me. But instead of doing that, route summarization talks about the fact that here we have /23. So the subnet mask here is 23. And in fact, if we convert this number, if we convert this to binary, 16 is actually 0001 and then 0000. Right? 18 is like 1, and of course you add 2 to it, so it's like this. And then 20, you add 2 to this, so it becomes 001, 01, and so on. Okay? So if you look at these numbers, they all have common part. So this part is common. Or maybe better yet, this part is common. Okay? So you'll find the part that is common, and then I can reduce the subnet mask from /23 all the way to /20. So this way, what I have essentially done is that I have grouped all these subnet addresses into one address, and we call this route aggregation or route summarization. So instead of sending how many, like 7 different route information for each of these networks, I send one route information to the internet, and whoever wants to send to any of these networks, the IP address will match this part. The IP address will match this address with the prefix, with the new prefix. So we can try it. So if you want to send to an address like 200.23.18, okay, .100. If we want to send to that particular address, does this address match? Of course, this address is part of this network, right? So does this address match with this? Yes. If you calculate the first 20 bits from the left-hand side, they match. So any address of any host under any of these networks will match this this route, which will allow me to summarize. So this way we can reduce significantly the size of the routing table. There's no point of having 8 different routes in the routing table if we can just group all of them into one. Okay? So anyone who wants to send to any of these subnets, he can send to me using this address, and I will be able to route it accordingly. So can we actually, in that case, kind of move any of these organizations to this part or this ISP? So imagine like I have a network at QU, and QU has taken some address allocation from an ISP service provider or something, and this address is happened to be 20.23.20.200.23.20.0/23. But then QU decided that they want to move from Ooredoo to Vodafone. Okay? So the question is, I have 2 choices now. Either I switch to Vodafone and switch all the routers and reset all the routers inside QU and use new address allocation, which is in this range. Okay? Or do I have the option to maintain my address allocation in that case, which is, in this case, will be 20.200.23.20.0/23.
If Ooredoo and Vodafone are connected, can they share the information? This is what I'm...
No, but you have, but in that case you have to route your information through Ooredoo. يعني ما ينفعش تقول مثلا the information coming to QU you will have to go to Ooredoo, and then from Ooredoo to Vodafone, and then from... No, if you have a service agreement with Vodafone, then your traffic has to come through Vodafone. يعني, so the question now is that, can I have this organization move here without having to switch the address or without having to change the address, because what happened now is that I did some route summarization. So the problem is now, does the route summarization affect this kind of change or not? So that's the question. Because if it does, then we have to be careful of doing route summarization. Because if I don't do the route summarization, I will send all the 7 routes. And if I move one organization from one service provider to another, all I need to do is just to broadcast or to announce this new organization is now under Vodafone. So I don't have to change much. But now, with this route summarization, is it going to work or not? Well, in fact, is that it's going to work. So if I have an organization, like organization 1, which moved here, they can maintain their own address allocation. So now, this service provider is going to announce this route, which will be common for all these networks. So now, this service provider will announce the old one in addition to this one. Okay? So now, if we were to assume that we have a router here, and there is an incoming traffic, and then I said, okay, so let's send to an address which is 200.23.20.100. Where will this go to? Well, this is clear. This we will have to match it with this. And if you calculate the match, it will not match because this is /23. Okay? So this will, in that case, will have to go here. So type. If I were to have an address which is 200.23.18.100. Okay, so now, where does this one go? Should it go here or go here? So now they have established an extra rule because in that case, this address will match both, right? So in that case, we will apply the rule that we will activate the match with the longest subnet mask. So in that case, it will go to the right location. So by having this rule, we can now use route summarization without affect this kind of moving from one service provider to another. So route summarization does work, and it does not affect a move like this, okay, which is kind of interesting. So by having this matching based on the longest subnet mask, we can override and we can overcome situations like this. Okay, مفهوم? Any questions? طيب. So this is for IP address version 4. Of course, in the network layer, there are multiple protocols that work together. We have IP version 4, when we have ICMP, which we will talk about, and we have also some routing protocols, or OSPF and EIGRP or RIP and so on and so forth. So these we'll talk about later on. So now we will talk about ICMP, which is used for error reporting and for ping and trace route, which is used for troubleshooting the availability of a host or a network. So when I use ICMP, I usually use it as part of ping. So if I want to, for example, check the availability of a remote host, then I can ping to that host. What happens is that I trigger the send of what we call echo request. And this echo request is a message that gets propagated throughout all the routers until it reaches to the final host. And if the host is running or is allowing ping, then this host will send me an echo reply with type 0 and code 0 to indicate that everything is fine. And in that case, the host is there, and I know that the host is available. If you want to make sure a network works, what do you do? بالضبط, برافو عليك. So you ping, in that case, you ping the gateway of that network, which is the the IP address that's assigned to the router interface itself of this network. If that replies with a ping reply, this means that the network is working. Okay. Other than this, if there is an error, then the error has the possibility of one of these values. So if the error is 3, this indicates network or service unreachable. And this has different levels. So you can have a network unreachable, host unreachable, protocol unreachable, or port unreachable. And these are different levels. Okay? So network unreachable, this means that the ping request or the echo request has passed through a router, and the router cannot find in the routing table any address that points to this host. There's no match in the routing table. Okay, so in that case, the router itself will reply with an echo reply with the type 3 and error code 0, which indicates that the network itself of that host is unreachable. I cannot reach to there. Okay, so host unreachable, this means that the router that this host is connected to cannot find the host on this network. Okay, so there is a slight difference here. There is a difference between I cannot find the entire network, or I can find the network, but the router that's connected to this network cannot find the host connected on this network. It's supposed to be directly connected, but it's not there. So in that case, I send host unreachable or protocol unreachable. This means that it arrives to the host, but for some reason the TCP/IP stack is not working fine. So in that case, I get an error back that the protocol is unreachable, or the port is unreachable, which means that the application that is running in the application layer that is responsible for responding to the ping command is not working or is not running. And that sometimes happens if the host opts to not reply to pings. Yani some servers, they keep themselves hidden, so they don't want to respond to pings, so that they become like hidden. That doesn't mean that they are not working. They are working, but they choose not to respond to pings, okay, for security reasons or something. So in that case, I get port unreachable. So sometimes port unreachable does not indicate a real error, because this indicates to me that it arrived to the host, but the host choose not to respond to the ping. Okay, type. So there are some other, what we are concerned with is these error messages, and this one actually, because this one is very important. TTL expired or time exceeded, and this error is used by what? Hadar? This error message is used by yeah, this is part of this is used as part of traceroute. So so ping tells you whether the host is running or available or not. Traceroute gives you the probable path to this host, not just the fact that the host is available, but how can I reach there? What hops will I go through in order to go to that host? So it gives you the probable path, not just the final answer from the host. So for traceroute, what happens is that if I want to know the probable path, then the technique is very simple. What happens is that I send an echo request. So you have the host, which is connected to a router, which is connected to a router, and so on. And I keep doing that until I reach to the destination. So what happens is that this source will send an echo request message with a TTL of 1. What does that mean? This means that when it goes to the router will decrement the TTL, and it reaches 0. What will happen? It will send an error message, TTL expired. I will not take that as an error. I will take that as, okay, the first hop, the IP address for that host, or the IP address for this interface is this, and actually the delay, the round trip time took this much and so on. And then I send another message with a TTL of 2. Okay? And I keep doing this until I get something other than a TTL expired or time exceeded. If I take an error, if I receive anything other than TTL expired, then this is an indication to me that I have reached the host. So in each line, if you perform this command on Windows or something, each line will give you the hop that you have to go through in order to reach to that host. And not only that, the final round trip time that it takes to go all the way and come back. Okay, so that's usually used for troubleshooting. So as a stopping criteria here, the UDP segment eventually arrives at the destination host, and destination returns ICMP. By UDP, we don't mean actual UDP from the transport layer. We actually we indicate datagram, which has no established session or no established connection. But in fact, ICMP works directly under IP. UDP is not in the picture. The UDP itself does not. ICMP does not use UDP. That doesn't mean that ICMP uses UDP. لا. Actually, ICMP is sent on top of IP directly. So in fact, in many cases, people get confused that in the network layer, you have the network layer and you have the transport layer. Okay, ICMP is here actually. Is between the network layer and the transport layer. So ICMP gets sent encapsulated inside IP directly. Okay, so there is no ICMP and then UDP. No, we don't do that. طيب, if we get port unreachable, this means that we have at least arrived to the final host, and then we stop. We don't increment TTL and send another echo request. We stop at this point. And in that case, this will be the final destination from. So that's how we use ICMP for troubleshooting using a ping and trace route, basically. Any questions? Okay. Type. IP address version 6. What is the motivation? Well, we know that the motivation is the address space. That's a motivation. That's a big motivation. But actually, there are some additional motivation. The additional motivation include the fact that we know that in IP version 4, there was some overhead processing the header. We had some complexity in the header itself, like the options field, like checksum, like fragmentation, all these things. So can we think of ways to kind of simplify this? Which will be the way to go for IP version 6, because we know that by increasing the address size from 32 to 128, we know that this will have implication on the complexity for sure. We want to do that still because we want to have bigger address space, but this will have an implication on the complexity. So can we compensate for this by simplifying some other processes that IP version 4 was using or was actually performing unnecessarily? And the answer is yes. We can do that. For example, as we said before, for IP address version 6, we removed fragmentation completely. We got rid of it. So there is no fragmentation in IP version 6. Type. We don't use options fields. Well, in fact, we can use options fields, but we do it in an indirect way. Okay? But the header itself does not have options field, which means that in that case, the header itself is fixed. So we don't need to have header length. Okay? So the header itself is fixed. It's 40 bytes, of course, instead of 20 bytes because of the address, because of the larger address. But we don't have to have header length. We don't have to have variable header size. And then along this path, we have also tried to enhance the functionality of IP. So, for example, we have removed checksum because the checksum requires the fact that at every single hop, what we do is that we have to calculate the checksum and detect whether there is any error in the packet or not. Okay. If we remove this checksum, this will reduce the processing time. صح? Because we don't have to calculate the checksum at every single hop. But if the packet has an error, what is the point of sending the packet all the way to the final host? And then we perform the error detection at the final host, which will be too late at this time. They have debated this, and they have found that, by having more reliable networks, which is what we enjoy nowadays, the possibility of having an error along the path decreases drastically. So the complexity or the overhead of processing the checksum overweighs the possibility of having to send a packet in error all the way to the final host. They have calculated the pros and cons of each one, and they have found that it's better to just remove the checksum because this will require significant amount of processing time at every single hop along the path. So it's okay. So how many times does this actually happen? Very few times. Okay, so let the packet go through until it goes to the host. And that doesn't mean that I will receive anything in error. This means that I'm delaying the processing of this until it gets to the final host. So I do it one time as opposed to I do it at every single hop. Okay? So in that case, they have removed this, from the header, which has simplified the processing of the header significantly. Type, but they have also thought about adding very important concepts like quality of service. So, IP address version 4 itself, as we said before, is best effort. Although there is a clear header field in IP version 4 called a differentiated services. There is a big field called differentiated services, which has some packet priority, which is what we call differentiated services code point. Okay, and this is clearly a priority. But actually, IP version 4 does not have any description or details how this field can be used. So they added that, but they left it to the developers or to the implementer on how to use that field. If you want to use that field to provide quality of service, it's up to you. But it's not part of IP version 4. That's why there are some, RFCs came after this to try to make use of this. Make use of this field to provide quality of service. They have found that this field can allow them, in a way, to provide quality of service. However, they have found some shortcoming, that this is not enough. And they have pointed this out in the RFCs, that, it's good to have priorities and stuff, but it's not enough. Why? Because not only do we need to use prioritization for the packets, but we also need to provide quality of service per flow, end to end. So if you have a source, and this source sends multiple flows. This can be audio, video, text, graphics, so on and so forth. They can belong to one application or two applications or three applications. So these applications, they produce certain flows, okay? And then, if you have a router here, you need to be able to differentiate between these flows, okay? So the priority will not be enough in that case. What you need to have is an identification for each of these flows. In order to make a decision at the router, to differentiate between these flows. Okay? So that's why in IPv6, they have enhanced the quality of service support by adding, in addition to the differentiated services, they have added something called flow label, which we will see in a minute, which can be used together with the differentiated service to provide more granularity on differentiated services between these flows. So we can, in fact, differentiate between these small flows end-to-end and provide end-to-end quality of service which is different for each of these flows, which is what we want, because the priority is based on a certain application. But we want to break down this application into multiple flows and differentiate between each of these flows based on the characteristics of these flows. For example, video will have different requirements than audio, than text, than graphics, and so on. So we want to be able to distinguish between these flows. And this that's part of what IP address version 6 tries to do. So with this introduction, we can then look at the header. As we can see here, if you compare this with the header format of IP, what do you notice? It's a lot simpler, right? So you see, it was very crowded, and now it's a little bit less crowded, which is exactly the main reason for designing IP version 6 in this way. So some of these fields still match what IP version 4 has, and some of these fields have been introduced and they do not have any corresponding fields in IP version 4, like this one, for example. The flow label did not exist in IP address version 4. The flow label identifies a flow end-to-end. This flow label identifies a flow end-to-end, which can be used together with the priority to provide quality of service on the flow level. Okay? Type. Okay, so the flow label, as we said, you have a source, and the source generates multiple flows. So each of these flows, we need to distinguish between them. We need to provide differentiated quality based on these flows. So IP address version 6, IP address version 4 did not have any identification for a flow in order to provide differentiated services based on the flow. So IP version 6 tried to fix that problem by adding, in addition to the priority, they add a flow label which identifies the flow. Remember, حتى in assignment 1 we had like one of the fields was flow and it was 0 and okay. So IP address version 4 did not capture any identification for a flow. Okay. IP address, remember, the IP address identifies a host, and the host runs multiple applications. Okay, so there was no identity or identification mechanism for a flow. So here they added the flow label to identify a flow, and this will help us to provide different service, different quality of service for each flow if we want. If we want. Because as I said, people have studied quality of service in IP address version 4, and they tried to use that field, the priority field, and they have found shortcomings. They have found that this is not enough. They need more granularity and more degrees of freedom to be able to control and provide different differentiation levels between the different traffics. So they need extra information, and that's why they came up with the flow label to provide some identification of a flow, which will allow them to provide quality of service. The question that I was expecting, and I was hoping to get, is actually now we're going back to the kind of ATM, because if you remember, in the old ATM we have talked last lecture about ATM, and we have said that we store the state of an end-to-end connection and so on and so forth, right? We talked about this. So isn't this going to drag us back to this? again, the question is, now we have flow label, right? Type ATM used to have flow label or used to have some end-to-end session ID, which is similar to this. Okay, so are we going back to the same concept of ATM, or this is different? يعني فاهمين ولا؟ ها؟ Okay, يعني is it a regression that now يعني you are lying to us? You're saying no, we have to use IP version 4, which is more scalable and connectionless and so on and so forth, and then you throw the flow label to us and say, oh, okay, so we need the flow label in order to provide quality of service. So I tell you, okay, so we had this and you said that this is bad. So now you are, getting us back to this. Well, the argument here that they have kind of put forward is that the flow label is different from routing based on the flow. Here we use the flow label only to provide differentiated services, but we're not routing based on this. ماشي؟ فاهمين الفرق؟ We're not using this for routing, which means that we don't have to store the flow label in the routing table and use it for routing. Which means that we don't need to store the state of the flow in the routing table, because this will make the routing very unscalable. What we are doing here is just to use the flow label for quality of service, which is not for quality of service is not routing, is different. So this way, no, we're not affecting the scalability of IP. يا مفهوم النقطة دي؟ We're not really jeopardizing the scalability of IP. It's still connectionless. So having flow label in the header, it doesn't mean that we want to switch IP from a connectionless protocol to a connection-oriented protocol. That's not the objective at all. Okay? But we use that only for quality of service provisioning, which is totally different from routing. مفهوم النقطة دي كويس عشان ما يحصلش أي confusion. ماشي؟ طيب. طيب, we have next header is the protocol field. So some of these fields, they exist similar to them in IP, even if the name is slightly different. So for example, next header is actually the protocol field. The hop limit is TTL. Okay? Payload length is the same, address is the same. So that's it. So these fields are similar but with different names. And sometimes,
Why we need that payload length if it is fixed?
Now remember, in IP version 4 we had two lengths. We had header length and payload length. Here we have only one, because the header itself is fixed. So you're thinking correctly, but here, because the header is fixed, we don't have the header length. We have only the payload length. And the payload length, again, is the length of the header plus date, similar to IP. Hop limit is, the name has changed to reflect really, because time to live was kind of misleading. It's not the time, it's actually the number of hops. So they put the name and they used it in a wrong way. So now it makes more sense. It's the hop limit. Okay? Why they use the name next header instead of a protocol? A protocol, because protocol refers to the protocol in higher layer. But in fact, as we will see in a minute, the next header might indicate a protocol in the same header. So we are going from IP version 4 to IP version 6, or from IP version 6 to IP version 4, which is in the same header. Why do we want to do that? We'll see. So that's why it's kind of recursive. Next header, it's kind of recursive. So you have a packet which is still in the same layer, and you are moving from one protocol to another protocol in the same layer. And that's why we call it the next header. Okay? So these are the changes. So they have removed checksum completely, which is what we have discussed. They have removed options fields. And now we have ICMP version 6, which in addition to ping and traceroute, we have some other types of messages like packet too big, which is the workaround when you don't have to do fragmentation. Sometimes if you estimate the packet size from the beginning based on the shortest maximum transmission unit along the path, and that turns out to be wrong. So in that case, maybe you end up with a packet which is too big. So in that case, you can send back an error message to the source to force the source to do like proper segmentation from the TCP layer, because in IP we're not going to do any fragmentation. So you have to do segmentation properly from the TCP layer in that case. Okay. IP version 6 does not have broadcast. But they have hacked this and called it all-node multicast, which is essentially similar to broadcast. But there is no concept of broadcast in IP version 6. So some other messages in ICMP version 6 include the multicast group management, like when you add a node to a multicast group, remove a node, or join, or disconnect from a group, and so on. So that's also part of ICMP version 6. Okay, so now the question is, can we apply IP version 6 right away? Well, of course we can, because this means that we have to close down all the routers on the internet, and next day we have to open with version 6. Because, as we said, the basic idea of a protocol is that we have to use the same protocol in order to be able to talk to each other. So if I change to version 6 and remove version 4, all the people I'm communicating with, they have to use the same IP version 6, which cannot happen overnight. So that's why they have a plan for migration, or a plan for transitioning between IP version 4 and IP version 6. During that transition period, which is what we live nowadays, and this will remain for another at least 5 to 10 years. At least 5 to 10 years, IP version 4 will still be around. So we need to have coexistence between IP version 4 and IP version 6. We will have to live with both of them coexisting sometimes in the same network and in the same geographical location. So how do we deal with this? Okay, and there are some mechanisms that facilitate this kind of transitioning. One of them is what we call dual stack, and another one which is what we call tunneling. So by dual stack, so dual stack simply means that we have IP version 4 stack, which will include IP, which will include ICMP version 4, which will include RIP version 4, OSPF version 4, EIGRP version 4, and so on. All these will be the baseline for IP version 4 stack. And also we have IPv6 stack, which will include IP version 6, ICMP version 6, RIP version 6, and OSPF version 6, and all of this. Okay, and these dual stacks both stacks will exist in a node or a router. What does that mean? This means that this host or router, they can be part of an IP version 4 network or IP version 6 network. Okay, but you have to choose to either use communication through version 4 or use the communication through version 6. Okay, type. So this means that if you have a host and you have a network which is IP version 4 and IP version 6 network, and they coexist in the same geographical location, dual stack will allow you to be part of this network or this network. Okay, but dual stack will not allow you to communicate between the two. So to communicate between a network IPv4 and IPv6, you kind of have to jump from this stack to this stack, or from this stack to this stack. So in that case, the dual stack itself will not help you to do that. So you need a different mechanism, which is what we call tunneling. Okay? So we need to explain what tunneling is, but we need to probably... Lisa? It's for 5 minutes. Eh? Okay. خلاص, we'll explain tunneling and then we'll start. So, tunneling here promotes or supports extra encapsulation. So we said that from one layer to going down, what we do is that we encapsulate, right? We do encapsulation. Remember encapsulation? So tunneling supports encapsulation in the same layer. So instead of using encapsulation to go from higher layer to lower layer, you use the encapsulation to stay in the same layer, but you move from one stack to another. Okay? So the way that this is done, so this explains how the tunneling is actually working. So basically, what happens is that the way that you deploy IPv6 is by saying, okay, I want to deploy IPv6, but I cannot say that I am IP address version 6 enabled totally, because the ISP has to support IPv6 in order to communicate to them. So what happens instead is that as an internal network, you can be IP address version 6, but you have to have a router here, okay, which uses some kind of tunneling to convert from 6 to 4 in order to talk to the ISP. Okay? And then the packet will go through that tunnel, which will make it IP version 4 now. And then it can be carried through the ISP. The ISP will carry it as IP version 4 packet. Okay? So it will be able to follow through until it reaches to the final destination. And then the final destination will be IP address version 6 network, which will then support decapsulation. And then we can communicate with another network, which is IP version 6. So this will allow me to move from one stack to another and then go back again to do. So this will entail the fact that we do extra encapsulation and extra decapsulation to facilitate or to provide this tunneling effect. Mm-hmm.
ISP support the IP version 6, so we don't need the tunneling, yes?
Yes, of course, yeah. If but actually what happens is that ISPs, they typically use IP version 6 inside their core network, but also when it comes to gateways, usually they still use IP version 4, okay?
So in that case, the throughput will be less because encapsulation and decapsulation.
It's an extra level of encapsulation and decapsulation, which for sure will affect the performance slightly, but it will facilitate. Yes, it will. Of course, here the overhead is justifiable because, well, you need to move from IP address version 6 to 4 and the other way around. So that's one of the seamless ways. You know what's the other way? Or another possible way that can be used to, not the tunneling, but in that case, you can move from the IP version 4 stack to the IP version 6 stack without having to do the encapsulation, is to do translation.
Correct.
So you don't do encapsulation, but what you do is that you convert the IP version 6 header to an IP version 4 header. But this will entail what? This will entail that you have to have mapping between IP version 6 and IP version 4. Okay? Similar to NAT, network address translation. They use translation to transition from IP address version 6 to IP address version 4 and the other way around. But it's not a common, it's not a good way. Because network address translation has lots of issues. Even within IP address version 4, it has lots of issues. Because it violates the layered stack. It actually violates the layered stack. Because in network address translation, you are trying to hack IP to use not only the address and the port to provide network address translation. So you are using information from two different layers. So that violates the fact that the layers are isolated, or there is some separation between the layers. So it kind of violates the layer stack, and it has some issues. So the network address translation table is separate from the routing table and all other tables, right? So you have to have a table which provides this mapping. Here, we don't need to have any extra table, right? Here, we are doing just encapsulation and decapsulation. We don't need to, everything is still stored in the packet itself, right? So we don't need to have an external table to facilitate this, right? But for network address translation, we'll have to do that. So in fact, there is NAT 6. There is network address translation version 6, which is used in that case not for switching from private to public, no, but switching from 6 to 4 or 4 to 6. So the purpose here is different. However, this is not as efficient and as common as tunneling, because tunneling is a concept that's used even in security, by the way. And it's proven to be efficient. You don't have to have an extra information or external way of mapping between the addresses or between the header fields. Here, everything is stored in the packet, which makes the transition from one stack to another kind of seamless. So within this part, you are seeing everything IP address version 4. Forget about IP address version 6. So here, the next header will be a IP address version 4, which indicates that you are actually moving across the layer, not down. Sorry, not down. You are moving a horizontal in that case. So the next header might point to horizontal movement from one protocol to another in the same layer, or it might point to a protocol in the higher layer or the lower layer. Okay, type. So this is with regards to tunneling. So basically, this is the logical view of the tunnel. So between here and here, we are communicating IP address version 6, and the tunnel is kind of a logical view. But in fact, if you look at the physical view, you have IP version 4 routers which are hidden completely for the IP version 6 communication. Okay? So that's how the tunneling is actually performed. So inside IP version 4, so this is the version 6 header, and then I encapsulate the header inside version 4. So the red header here is a version 4 header, and the communication is facilitated through this network as usual, IP address version 4. And then when I go here, I will do extra level of decapsulation, and I convert to version 6.
Doctor, one question here: how the QoS will be delivered? Because now it is code inside this one, and prioritization, everything will not be done at this level.
Prioritization
means priority will not be given to this one, no sir, because it is the part of IPv6. So when it is encapsulation done, then this will go below this one. So how here it will be done in that case? Between these three intermediate.
All the prioritization and everything will be done based on the network version or the IP version. So inside this network, the prioritization will be performed using the IP version 4. And then when you go here, when you do a decapsulation, you go back to the original header, yes. Okay. So you perform the prioritization of IP address version 6, which might include the flow label and all this stuff. So even quality of service based on labels and stuff can be still done within IP address version 6 network. Once you switch to IP address version 4, you can do prioritization only, not based on the flow, but based on the differentiated service field inside IP. But then when you switch back, when you do decapsulation, you can go back to IP address version 6 and perform quality of service in any way you want for IP address version 6. Okay? I see people stretching, so that indicates that we need to kind of stop. So we covered the IP datagram and the header format and ICMP and IP version 6 and the transition between them. Now, what's left is to talk about routing protocols. And routing protocols, they are used for dynamic routing, where the routes are updated between the routers automatically to facilitate the routing of packets from source to destinations, or from source network to destination networks. The routing protocols are divided into what we call link state routing protocol or distant vector, and we'll talk about the difference between them. And there is, of course, the hierarchical routing, which uses two levels of routing, which includes border gateway protocol that we will also discuss later. So in terms of classification for these routing, so basically, as we have discussed before, we have the concept of forwarding, which is done as part of the routing path end-to-end. So first, routing will allow you to estimate the end-to-end path, and then when the packet moves along that path, each hub will perform forwarding to forward the packet along this path. So in order for us to perform the forwarding properly, the routing protocols, they need to form these forwarding tables. And there are two ways to form this table, or to create this table at every single router. We can, of course, create these tables manually. And in that course, we refer to the concept of static routing. And of course, static routing is not efficient enough, because the network topology changes frequently, and the manual creation of such tables will become a headache every time the network topology changes. So we know that this is not practical. So we use dynamic routing protocols. So we use one of the dynamic routing protocols like RIP, OSPF, EIGRP, and so on. And these are divided into two main types, as we said, the link state versus distant vector. So for link state routing protocols, basically, the basic idea, and I'm not sure if some of you, they have some idea about the difference. For link state, what the routers themselves, what they send to each other is actually the state of the directly connected networks. Okay? They send to each other a state. And each router eventually will have the state of all the links in the network. They form a state table. This is different from the routing table. Okay? So link state routing protocols, each router will have a total view of all the states of all the links inside the network. And they have a link state table, which lists all the state of each link. And we'll talk about what state of link is. Versus for distant vector, we don't have to have a global view of the entire network. Each router will send local information to the router next to it, and the router next to it will kind of consolidate and send to the one next to it, and so on. So one router does not have global state of all the links, but it can estimate the cost of a specific path incrementally, but it does not have global state of all the links inside the network. So if this router sends the distance of all the networks connected to it to this router will say, okay, I will accumulate the distance of this network to what I have before I send it to the one next to it. So the distance keep incrementing, but you are not storing any states inside. So in that case, the router does not have global view, but it has some incremental information which is kind of consolidated or summarized. So the distant vector protocols are slightly more scalable in that case because they don't have to maintain global view of all the link states inside the network. So this is the basic idea. So for link state, we have link state table and routing table. But for distant vector, we only accumulate the distances in the routing table directly. So we don't have to have a global link state table before we estimate the cost in the routing table. And this is the basic idea, but we will, of course, discuss it in more details later. So as a quick introduction to all the dynamic routing protocols, people usually or typically, they map routing protocols to graph theory or graph operations. So the best way to understand routing protocols in the network is to map a network to a graph, which is basically composed of set of nodes and set of edges. So the node corresponds to a router, and the edge corresponds to a link between two routers. Okay, and based on that, the network will have this set of nodes, U, X, W, and so on, and we'll have this set of edges. So in that case, if we need to, for example, calculate the cost from for actually going from U all the way to W, well, then we can say, okay, we can go UVW, or we can go UW directly through one link. So the cost of UVW is 2 plus 3 is 5. And the cost of UW directly is also 5. But we will go through one hub in that case. So the cost of any path is the summation of the cost of every single cost of the links through this path. Someone might ask, what is the cost? What is the cost represent? So that cost represents what on the link? The cost represents the amount of effort that you have to spend in order to go through this link. So obviously, if the link has greater bandwidth, the cost will be less, or the amount of cost that you have to pay to go through this link is less, which means that the cost is reversely proportional to the bandwidth. Okay? If delay is more, then this means that you have to pay more cost, right? So it's kind of the cost or the penalty that you have to pay in order to go through this link. And the higher this cost, the lower the resources that this link can give to you, okay, in order to go through this link. So the cost is something that you pay. So graph theory or graph abstraction or graph representation is also used in many other fields, not just routing networks is used in peer-to-peer networks, and we have discussed that before, and we can look at the peers inside the network. Regardless of the physical network topology, we can look at peers as graph. Each peer is actually a node, and when one peer sends to another peer, that's an edge. Okay? And this way we kind of ignore all the underlying topology of the network. So we have just connection between peers. Or TCP connections. We have a big internet, and we have TCP sessions which are established between a group of nodes. So again, regardless of the underlying network topology, whether it's wireless, we don't care about this. We just need to study the end-to-end sessions of TCP between different nodes on the internet as a graph. Okay, so we abstract it in a form of a graph, and we study the performance of these sessions end-to-end. And then we abstract all the network stuff into a cost. Okay, so the cost of this TCP session is X, and the cost of this TCP session is Y, something like that. And then we can form or represent these TCP connections as a graph and study, because then there are some tools that allows you to study this graph very efficiently and be able to estimate total costs and be able to estimate, for example, how you partition the graph into two graphs and so on and so forth. There are some tools and techniques that are very sophisticated in graph theory that will allow you to study the performance of the network very efficiently. Okay, so that's what we will do. So the cost of a link is the cost of this link, but the cost of a path is actually the cost of all the lengths associated to that path. So when we go from one node to another, now the problem is that we have multiple ways to go from one node to another. So routing protocols will allow you to select the path that will give you the minimum cost or the shortest cost, which is what we want, because we want to select the shortest path that we can use to go from one node to another. So basically our objective is to find the least cost path to go from one node to another. So again, that can be done using either link state routing protocols or distant vector routing protocols. So there are two different algorithms that we will study. One is the Dijkstra algorithm, which is used by link state routing protocols, and we will study this algorithm and analyze it from a performance perspective. And we will also study the Bellman-Ford algorithm, which is used by distant vector routing protocols. Okay, and we will analyze it from a performance perspective, and we will be able to study the difference between these two techniques in that case. Okay. So in terms of classification of these routing protocols, we have global or centralized or decentralized. By global, we mean that we maintain global view, which is what we call the link state routing protocols. So link state routing protocols keeps a global view of all the states of the links in a separate table before you estimate the shortest path. Okay? Distant vector or decentralized, we try to not consolidate all the global view of the network, but I will have a local view, which is all the networks that are connected to one router, and then I can send this to the next hub only. And then this next hub will consolidate the information that it sent with the ones that's directly connected to it into one local view, and then we'll send this to the one next to it, and so on. And we keep doing that until we will be able to calculate the total distance incrementally or gradually. But again, we do not have a global view of the entire state. Yani if you ask one router in distant vector routing protocols, what is the state of link X? I don't know. But what is the cost to send from your node to host X? I give you the distance, the total distance. But that doesn't mean that I have a state of a particular link and how this link has bandwidth or delay or something. I don't have this state. مفهوم الفرق؟
Which more efficient according to cost or something?
Well, we will study the different issues in each one. Right off the bat, I can tell you that, of course, any decentralized algorithm is essentially better because I don't have to consolidate and integrate global view of the entire network, because in some cases this might be prohibitive, right? So to wait until each router in the network to have global view of the entire network, that requires a significant amount of time, because the states have to propagate. In link state, they use flooding. So the state of one link will be flooded to the entire network. So until you get a unified picture at every single router, that requires significant amount of time. So in that case, decentralized is more efficient. If it can give you the least cost path as efficient as decentralized. Because we know that if one router has the global view, then it can easily get the shortest path from any node to any node, right? So we know we have all the information. We can calculate that. We can use some optimization. We can, worst case scenario, we will do exhaustive search. صح? We have all the information. We don't have any problem. So we can do exhaustive search and get the answer. We can do it. Okay? The problem is that decentralized, if you have local view, how can this local view get you the optimal end-to-end course? You don't know. Right? So decentralized is always better only if it gets you the optimal path. So if we reach with the decentralized solution or the decentralized algorithm, which is essentially Bellman-Ford algorithm, if it can give you the least cost path similar to Dijkstra, then we'll go with that because it's better. It's based on decentralized. And the good news is that it does. But we will also talk about some small glitches and issues with that along the way. Another type of classification, which is static routing versus dynamic routing. And that's of course, clear. Of course, routes change slowly over time because it's done manually in the case of static routing. And every time the topology changes, we have to change, which is not practical. So we need some kind of dynamic routing protocol, which requires periodic updates. So the routers, they will send either the state or the distance of the directly connected nodes periodically. And in some cases, because periodic might be a significant overhead, sometimes we use it event-based or triggered. Sometimes it's based on some trigger, as we'll see. Okay? So now we'll talk about link state and we'll leave that to next time because that requires a really fresh mind. I wanted to stop here so that next time we'll have like a fresh mind and we can really focus and concentrate on this.